Dude, I put the team on my back too.
All right. Okay, you might notice I put a couple assignments up, but I don't think you're quite ready for them yet. I want to just kind of finish this example up. Maybe do one more, and then I think I can unleash you on these assignments. I'll give you a couple days work. Okay, so unfortunately, we didn't get through that one yesterday, so we kind of have to catch up to speed where we were. Remember, we were looking at this problem, right? This is where we left off. Remember this guy. We're trying to find. What's that? Okay. Trying to approximate area under this curve. F of x equals x squared plus 1. We're going to cut this thing up, this region up into, what do we say? Yeah, 24, so pretty small rectangles, and we wanted to come up with a formula, right? That's going to, using sigma notation, that's going to give us that approximation. And so we relied on some stuff we had talked about. Remember, we had said, I think we went back maybe one more slide, and we had tried to define completely generally. We want to define the area of the ith rectangle. And based on the area of the ith rectangle, based on the right side, the height is based on the right side, agreed? Because remember what we said was the location of the right side of the ith rectangle occurs starting at A and taking I steps of width delta x to the right. Agreed? Okay. So we could call this position right here. We could call that x sub I. And we said that has to equal starting place plus my I steps, the distance of my I steps, right? A plus I delta x. And so then the area of that rectangle is simply going to be delta x times whatever the value of the function is at A plus I delta x, right? And so our job is just to find out, right, so there's the area of the ith rectangle. The value of the function at x sub I times delta x. Our job is just to find out, well, what is that going to look like for whatever curve it is we're working with, and then add it up, okay? And so we did, we started to. Here's our function, n equals 24. We're going from 1 to 3, so delta x would just be, b minus a over n gave us 1/12. 2/24 or 1/12. Our function is x squared plus 1, so f of a plus I delta x, which was 1 plus I delta x for us, ended up being that quantity squared plus 1, right? Which we began to FOIL out and add up. FOILed it out, added 1 to the constant, and now we're just going to go through the process of adding all those up. Relying on, and I just gave these to you, but remember I gave you these 4 summation formulas. They're in your book. And we're just going to use those to get answers via sigma notation, right? We're going to write our summation in ways that these sums are going to pop out. Okay? And where we left off was we left off right here. Okay, does that make sense? Does that ring a bell? Gotta get you back where we were. Okay, I took a little detour though at the end because I wanted to make a point about this. We got to this point and the question arises, and maybe you intuitively just know how to do this, but what do we do when we have a sum of a bunch of different terms? Okay. And to illustrate that, I took a little detour, and we were just going to look at a really simple case. What if we look at the sum of 2 terms? The sum of I plus the sum of the quantity I plus 1 from 1 to 4. That's a small enough sum that we can just write out each of the 4 terms that we get from it in sigma notation, right? And if we regroup those, if I just take the first term of each and group those together, and the second term of each and group those together, what do these look like? How could I write that one in sigma notation? That's the sum of what? I from, what's this one?
1.
Yeah, the sum of 1 from 1 to 4. What's the moral of that story? Going from there down to there. Yeah. Moral being you can separate those, can't you? Okay. So coming back up to this step right here, let's pick up there where we left off and continue on the next page. So we can break that into pieces then, right? We can break it into 3 separate sums. So let's do the first one. Sum of 2 from 1 to 24 plus. What do you suppose I can do with like that 1/6? And I can illustrate this with another little detour. You can, can't you? And we can see that pretty easily. Like, let's just take a 3-term sum. What if I have the sum of 2i from 1 to 3? That's just 2 times 1 plus 2 times 2 plus 2 times 3, right? Agreed? So that's, I can factor a 2 out, and that's just 2 times 1 plus 2 plus 3, right? And so that's really just 2 times the sum of I from 1 to 3, right? Okay, so I won't do this for all of them, but you get the idea that the same tools are available to us with sigma stuff, right? With summations that was for derivatives or antiderivatives, right? So we could write the second one then, this guy, as 1/6 times the sum of I from 1 to 24. And this guy right here would just be, let's pull the 144. Oh, and I have this 1/12, I guess, out in front of everything, don't I? Forgot that. Oh, we'll do that at the end. Plus 144th times sum of I squared from 1 to 24. And then we'll take the whole thing when we're done, I guess, and multiply by 1/12. Okay. Now do you see the point of all those summation formulas I gave you? Right? There they are, right? So we were able to, after expanding out the quadratic, I think we have a perfect square in there that we expanded. We expanded it all out and wrote it as a sum of separate terms. Because it was a polynomial in I, we're just going to get these different powers of I in each term, right? And so we can go back to these. Whoops, I went too far, I think. Way too far. Go back to those. Okay, we know what n is this time though, don't we? These are all written in terms of a sum of n terms, but n is 24 for us, so we're going to get numerical answers for each of those sums. So then what does this guy become? We get what's that? Cn, right? Was the sum of c from 1 to n was Cn, so n is 24, so that's just 48, right? What about this guy? Well, we're going to get plus 1/6 times, what was the sum of I, do you remember? Yeah, good, n times n plus 1, so 24 times 25 over 2, okay, plus 144, then I squared, that was a weird one, n times n plus 1 times 2n plus 1 over 6. Good, so that's gonna, what's that gonna be? Let's see, we're gonna get 24 and times 25 times what? 49, 2n plus 1 over 6, all times 112. And that's just a numerical expression, that's easy to simplify. So what are we gonna get here? Let's see, 6 and 24 become a 4. I could cancel the 4 and the 144 would be a 36. And, well, okay, it's pretty ugly after that, isn't it? Let's see, so this one here, I could cancel the 2 and the 6 and make that a 2. And so what do I get there? 48 plus 50 plus, yikes. So kind of ugly. What is that? What's 25 times 49 over 36?
Right.
So 5.67, so 5 2/3?
Yeah.
So 17/3? Is that right? Yeah. Wow, simplified that much? How'd that happen? Oh, 9. Yeah, 9. There's the 9s. What about that? No, that's not gonna. How did I simplify so much? That can't be right.
You're wrong.
25 times 49 over all over 36? Really?
Yeah. Wait, hold on.
Well, that's 7 times 7. That can't be.
Hold on.
Brian, well, let's go.
Brian,
It'd be 1,225 over 36.
1,000. What is it again?
1,225 over 36.
Okay, now that plus 98. Let's hit plus 98 divided by 12.
Let's go.
Oh, hold it. I messed that up, didn't I? We need to hit equals. So we figure out what that is.
1/12 times 9.
Yeah, the whole thing.
That would be Brian.
Well, that seems like an awfully big
Yeah, it is.
number. I guess maybe it's right. Dividing by 12 is going to make it. So you got 34-ish?
Yeah,
Wow, that seems pretty big. 34.4 or something ish.
4.3.
34.3?
03.
03. God, that seems, look at that. That seems pretty big. 3.
Yes.
3 squared.
No,
I'm
that's
getting
not
like
the final
1,000.
answer. That was just the 1,225 over.
Oh, that was just the one. Oh, okay, I want the whole thing. Yeah.
11.00.
Yeah, 5, that's what I got.
Yeah.
But this guy right here. What'd you get for the whole thing?
11.00.
Oh, that's better. Okay. So about 11.00.
0, 0.
Okay.
2, 3.
Okay, so about 11.0. Okay, that's better. That seems like more like the closer to the right area. Okay, now here's the next point I want to make about this. So you tell me, is that going to be an overestimate or an underestimate? It's going to be an overestimate, isn't it? Because we added up the rectangles based on their right-hand edges, correct? The function is increasing, so that's a recipe for a circumscribed sum, right? Okay, how could we come up with an inscribed sum of the same area? So what if we wanted to add up the inside rectangles instead? What's the only thing we would have to do differently? I mean, almost everything would be the same. There you go, right? All we have to do, if this is, would everybody agree that if we're going to call this x sub I, then if the right-hand edge of the ith rectangle is x sub I, what's the left-hand edge going to be called? x sub I minus 1, sure. And the only difference is, to get to that point, we're starting off at A, and we're going to take I minus 1 steps to the right. Agreed? So all we would have to do here is we would have to just make a trade from x sub I equals A plus I delta x to x sub I minus 1 equals A plus the quantity, plus the quantity I minus 1 delta x. That's a little harder, as you might expect, because you've got just a little more algebra to do, but it's not much harder, right? It's just, and it's going to give you, what effectively it's going to do is it's just going to trade out two rectangles, one at the beginning and one at the end, right? So I don't know if we need to necessarily go through that or not. You guys will get a chance to do that. Now, the notation we use for that is this. We would say that capital S sub n is the circumscribed sum, and lowercase s sub n, because it's a smaller one, is going to equal the inscribed sum. Okay? And so if we wanted to do something like, if you were asked a question like find capital S of 8, what do you suppose that's asking? Circumscribed sum of how many rectangles? 8, exactly. So does that make sense? That's going to define what your delta x is, okay? Based on however wide the area is that you're adding up. Okay, in either one of those cases though, where I really want to leave this thing is they're both imperfect. What we came up with was an overestimate. We could also, if we wanted to, we're not going to take the time to do it, but if we wanted to do the inscribed sum, we could get an underestimate and average the two, but even then it's not going to be perfect because this is not a linear function. It's still going to be off a little bit. How could we make this an absolutely perfect estimate? Any suggestions? Think about when we were playing around with those sums yesterday on the computer. What were our strategies for improving? Make more and more of them. Make them really small, exactly. How many would I need to get an absolutely perfect estimate? An infinite number. Now I can't use an infinite number because infinity is not a number, but we've done something in the past that might allow us to deal with infinity. Maybe you thought you'd left these behind forever, but how do you suppose we could do this? With a what now? With a limit. Aha, okay. How about that? With a limit.
Oh, God.
Right? So if we want to come up with the absolute area, and this is, by the way, this is called a Riemann sum. Okay, and this is a big deal. This is a necessary step, but the payoff is huge. Huge. Riemann. Riemann. This is a Riemann sum. The payoff is huge. By going through this step, and this is now, just kind of overlook the tedium of the algebra here because we're coming up with something super cool. We're gonna do something, that's gonna allow us to come up with a brilliant shortcut for finding areas under curves. And this is really as amazing and powerful as differential calculus is. This is even more so. I mean, this is a really, really big deal. So if we want to come up with an absolute area under the curve, it's equal to then the limit of the sum of the area of the ith rectangle. What did we say that was, right? That was just f of a plus I delta x times delta x, right? Everybody agree with that? All that is just the height of the rectangle at x sub I, right? Times the width of the rectangle. As I goes from 1 to n, as n does what? Approaches infinity. Okay? And that's going to give us an exact answer. Isn't that amazing? That's just totally amazing to me. It still is. I've done this for years and years, and Still just amazes me that we can do that. Seems like it shouldn't be fair that you could get something exact like that from a discrete process like this, but we can do it. Okay, so it's just not fair. Now let's go back to the last example because we've already done a lot of the work, right? So if we want to go back to this function right here, well, we've already, well, I guess we just have a 12 there, but really all we needed to do was just change that delta x a little bit, right? We've already done a lot of this stuff. So we'll just do the same one. So our function is x squared plus 1. What's that? Oh, I don't have a gold card. Should I have a gold card?
I thought it was like his, like, tardy supposed.
I know, it's like, good for you.
Okay, so if we're doing f of x equals x squared plus 1, and we're on the interval from 1 to 3, right? Then what's our delta x going to be this time?
It's gonna be something.
Yeah, what's our delta x going to be? We know it's going to be vanishingly small, right? In order to fit the curve perfectly, it's got to be, they have to have a width that approaches 0. What's it going to look like though? What's our formula for our delta x? B minus a over n, right? So for us, b minus a over n is just going to look like 3 minus 1 over n, so just 2 over n. Right, in the limit as n goes to infinity though, what does that delta x go to, obviously? 0, yeah, as it needs to. Okay, so then we could, so what is f of, and a is just 1, right? Right, so what does f of x look like for us then? Well, going to be the quantity
That was something new.
1 plus I times delta x is 2n, 2 over n, sorry, so 2i over n squared plus 1,
Look at these.
right? Everybody agree?
Yes.
Okay, so that's, this whole thing is f of 1 plus 2i over n. Okay, I gotta multiply that by delta x, right? And we're gonna take the sum as I goes from 1 to n, in the limit as n goes to infinity. Okay, so what's the order in which we do this stuff? Because we got a lot of layers going on here, don't we? We've got this, we've got a sum of all this stuff. What's the variable of the summation? I, isn't it, right? I is the variable of the summation. That's the index variable. So when we do stuff on the I is only, we're only interested in, you know, like if we ended up, for example, in a weird case, if we ended up with, well, like we will, no, we won't here, but if we ended up with x's in our summation, are those x's going to be acted on by the summation? No, they're not. The x's, as far as the sum is concerned, it's going to sound a little strange, as far as the sum is concerned, that x is a constant, right? The only thing that the sum is interested in are the i's via these summation formulas, and I lost them. I can't remember where back one more. Those guys, right? It doesn't matter if I have x's in here, the x's are unimportant. It's the i's that matter. If I had an x there, our result would just be this stuff times x, right? See my point? Okay. Now the limit, on the other hand, which is acting outside of that, we're going to work from the inside out. So first we're going to do the summation stuff. The sum is interested in the i's. What's the limit interested in? What's sort of the variable of the limit here? The limit is, we're taking the limit as what approaches something? N, right? So the sort of the variable, you can think of it that way, the variable of the limit is the n. That's the only thing it cares about. Everything else would be considered a constant from the perspective of the limit, right? Okay, that's a weird mode of thinking for you. It's very new, I'm sure, but I can assure you in future years, you're gonna amplify that a whole bunch. You're gonna look at things when you do multivariable calculus. Like let's say you're gonna do this kind of stuff. You're gonna add up areas or volumes under surfaces, right? Or you're gonna look at the fall lines. So you're looking at derivatives on the surfaces that are two-dimensional. Then you're taking derivatives with respect to x and y, but you're going to take partial derivatives where you're only differentiating with respect to x, y is constant. Partial derivatives with respect to y, where you're only differentiating with respect to y, and the x is considered constant. So this is a mode of thinking that you will do more and more of in the future. So let's kind of work our way out there. We've already done a lot of this algebra. Let's expand this out. We already did this stuff, right? If I expand this whole thing out and add 1, so everything in the pink bubble, what do I get back? Wasn't that 2 plus 4i over n? And we had 24 there instead of n last time, right? Plus 4i squared over n squared. Right? You see where I'm getting at too? That's just like a plus b squared. So I get a squared plus 2ab plus b squared. Does that make sense? Okay. So that's, and then we added the 1 to the 1. So there's all that stuff. So we'll break that into 3 different parts. You don't have to, here's the thing though, we did a lot of extra work last time. We don't need to necessarily even write this as 3 separate sums, do we? We can just treat each one separately. So this first one, if I do this sum, what am I going to get? Same thing as before, right? If I take the limit of 2 as I goes from 1 to n, what do we get back? 2n. Right, for this guy. How about this guy? Well, we can pull the 4 over n out front. What's the sum of I from 1 to n? Remember that one? Elizabeth's got it handy. Good. Times. Okay. Good. And then plus here we'll pull the 4 over n squared out front. And the sum of I squared from 1 to n, we said that was the weird one, n times n plus 1 times 2n plus 1. Over 6. And then I've got my 2 over n outside the whole thing, which I kind of lost track of. Oops. Right? Okay. Man, we use a lot of virtual paper here. This business. Okay, so time to simplify. Time to simplify. Let's distribute this 2 over n all the way through. At the same time, let's expand this stuff. Right? So if I distribute my 2 over n to this first term, what do we get? 4. Okay, what about over here? Well, I'm going to get, good, so I'm going to get 8 over n squared. Now, if I FOIL out the top, I'm going to get n squared plus n over 2, right? If I does that make sense? I'm distributing the 2 all the way through, and then I'm just
Oh,
right? See what we've done? Just expanding out the top. Okay? Okay, yeah, we're gonna do something with that. We're gonna factor an n squared out the top. And then here we can multiply straight across and get, yeah, so 8n, and then if I FOIL that out, I'm gonna distribute an 8n to that product. So this is gonna give me 2n squared. Let's write this in 2 steps. So we're gonna get 8n times 2n squared plus 3n plus 2, if I FOIL that out. All over 6n cubed. Okay, you're gonna see something happening here. Looks like a lot, but watch this step. 4 plus. If I factor an n squared out of the top, I could cancel those and make that a 4, right? I end up with 4n squared times 1 plus, what am I left with here if I factor out an n squared? 1 over n, aren't I? Right, everybody see that? Okay, or the other way of thinking about this is, you know what, maybe this is better. Hang on, let me backtrack a little bit. Instead, I think it's easier to see. How about if we just divide this n squared through to each term?
Okay.
Right? So we get 4 times 1 plus n squared over n is 1 over n. That's better. Okay? Same kind of thing here. Let's simplify the 8/6, so that's a 4/3. We can cancel one of those, right? So we end up with 4/3 times what? If I divide each of these terms separately by n squared, then I'm going to get 2, right? Plus 3 over n. Would you agree? Plus 2 over n squared, because remember that's a square. Now let's take our limit. What's going to happen in the limit is n goes to infinity. Every term with an n on the bottom goes to 0, right? So that's going to vanish, that's going to vanish, and that's going to vanish, right? What are we left with? Some constants. We're left with the answer 4 plus 8/3. So 8 plus 8/3, so is that 32/3? That's the exact answer under that curve. The exact area. About that. Yeah. So that's what you get to do next. Okay. It looks like a lot of stuff, but really it's not horrible. I mean, really all you're doing is right. This is the key part. You're always starting there, aren't you? Right? That's totally general. And then you're just going to evaluate that at a specific function for a specific value of a, and therefore it's also a specific value of delta x. Okay? You're going to simplify this, using your sigma stuff. You'll simplify the sigma stuff, right? And then you take a limit as n goes to infinity, and then all the terms with n's on the bottom are just going to go away. It leaves behind the answer. Okay? It extinguishes. This is pretty cool. If you watch this happen visually, when you let n go to infinity, and all of these, if you want to think about this using kind of a visual model, which I like to do, I think it's kind of helpful. When you do this step right here, as you extinguish those terms, that would be like letting the rectangles go to 0, and all the little parts that didn't match would just vanish as they went to 0. Those are the parts that were imperfect, right? That would have been the under or overestimate would just go away. All right. I think we're done. I don't think there's anything left for us to do before the next assignment. So, yeah.
So 2 minutes of
Yeah.
Just let it all absorb.
Yeah.
I'm just gonna
If I
stare
like
at it.
sleep